In the last class, we were discussing about the uh, time domain analysis of a control system. In that, we looked into the different kinds of input, the standard inputs. Then we analyzed a first order system. In a first order system, we saw that the control system will have one loop and one pole, and this pole it has to lie on the left side of the S plane for the system to be stable. Then the next was the analysis of a second order system. For the second order system, this is the block diagram with unit feedback. This is the open loop gain, and for the open loop gain with the unity feedback, this would be the block, and this will be the transfer function. And for this transfer function, depending on the zeta value, zeta here is a damping ratio, you have different cases how the system will behave. That is undamped, overdamped, underdamped, critically damped, and overdamped conditions. And for this, that is, we also found out the solutions of the circuit of the system under different damping conditions. For that is when zeta is 0, when zeta is less than 1, when it is greater than 1, or when it is equal to 1. Now coming to the next part, that we will be studying about the underdamped system, and we'll find the exact solution for this underdamped system. We saw the transfer function. This is a transfer function for the control system. For a second order control system, this was a transfer function, and the denominator equated to 0 will give the characteristic equation. From this characteristic equation, for this equation, for this part of the equation, because it is S square, it will be having two roots or two solutions, S1 and S2. And based on the solution for second order system, the solution is written like this. And let zeta into omega n, we know it is a natural frequency, zeta is a damping ratio. Let zeta into omega n be alpha, and omega n into root of 1 minus zeta whole square, let it be omega d. So then based on this, the solution S1 and S2, which are the two solutions, can be written as minus alpha plus or minus j omega d. Now suppose the system is given by that excited by a unit step function. What is unit step function? It is u of t, and Laplace for a unit step function will be 1 by s. So C of s will be r of s. This r of s goes to the numerator, r of s into omega n whole square divided by s square, s into 2 zeta omega n plus omega n whole square. So then what is r of s? R of s will be 1 by s square. It is going to be 1 by s square. Zeta here will be, the r of s will be 1 by s. It is 1 by s into s square plus 2 zeta omega n plus omega n whole square. This s comes to the denominator. Then using partial fraction method, this is a equation that we write: a by s plus bs plus c divided by s square plus 2 zeta omega ns plus omega n whole square. Then applying the partial fraction, continuing with the partial fraction, we know omega n whole square will be a into this half plus bs plus c into s. Multiplying, taking all the s terms to one side, s square terms to one side. We know this is 1 into omega n square, and we have a into omega n square, so a is equal to 1. Then s square, we don't have any s square term here, so a plus b equal to 0, so b will be minus 1. S term is also 0. On this side, we don't have, on this side of the equation, there is no s term, so 0 equals 2 zeta omega n a plus c. We know a is 1, so finally z becomes minus 2 zeta n. Then these values have to be substituted here for a, b, c. Substituting this, we get the c of s is equal to 1 by s plus minus of s plus 2 alpha divided by, here alpha is nothing but, what is alpha here? This is alpha. This term is alpha. These two terms represent alpha. These two terms represent the alpha value. That is omega zeta into omega n is alpha. So that is represented as minus 2 alpha, and taking minus outside, it is minus of s plus 2 alpha divided by the denominator. Now this has to be, this is in the standard form, but whereas this is not in the standard form, it has to be brought into the standard form. Again, here also this can be represented, this term can also be written as alpha. This is, again, see here, it is written, this term is written as alpha here. Then what this is s plus 2 ab. We don't have b square, so what is b? A square is here, but what is b square? B square is alpha square, which is not there, so add and subtract alpha square. Then it is s plus alpha whole square, then s plus alpha whole square. Then what do we have? This term, it is, here we will have s plus alpha, I'll just write it as some x value. This is whole square, this whole square, then plus omega n minus omega n square minus alpha square. I don't have alpha, instead of alpha I've just written it as x here. Now whole square, it is to the power of here, it is to the power of, I've just shown it as multiplication, it is actually to the power of. So this value, this term, writing it here, omega n whole square minus alpha square. Alpha square is zeta square, omega n square. Take omega n outside, it is 1 minus zeta whole square, which is nothing but omega d whole square. So now substitute this here. You bring it to the standard form. Stop substituting, then this is one term. This part represents this half is 1, and this will be the other term. So divide it now, then this represents the cos term and this represents the sine term. So this is in the now standard form, standard Laplace form. Take the inverse Laplace. So this inverse Laplace, this is c of t. Here we have to write it as c of t. This represents c of t. This is not 1 by s, it is nothing but here s, I mean 1. This value is 1. This s is not there. This s value is not there because it is now c of t here. This is c of t. C of t equals, so c of t equals 1 minus e power alpha t cos omega t plus, here can we directly write it as sine omega t? It cannot be, because we don't have omega d, so it has to be multiplied. You'll have to multiply this term by omega d and you'll have to divide. Then this term will be remaining. This term will be there. So that is written here into alpha e power minus alpha t sine omega t. Then this term here, this alpha 1 divided by omega d, alpha is eta zeta omega n divided by omega n root of, this is root of 1 minus zeta whole square. So that becomes zeta, this omega n cancels, it is zeta divided by root of 1 minus zeta square. Again, substitute for this. This has to be substituted in terms of this equation. Now substituting, see, this part is substituted by this equation, you get this. Now take out root of this, take out this outside. When you're taking out outside, it has to be multiplied with cos term. When you're taking out this, here it has to be multiplied with cos term. Then multiplied with cos term, Here, this part, this can be represented as sine theta and this can be represented cos theta. So you have sine theta cos omega dt plus cos theta sine omega dt. So this is nothing but sine A plus B. So represented like this, sine A plus B. And this is the final expression for the value that we have for the overdamped condition. See, sorry, this is what, yeah. And this expression here, it is very important. This expression is very important here. The expression for underdamped condition, this is for the underdamped condition, this expression whatever we have here is very important, which you have to remember, because we'll be using this again while doing the time domain specifications. Next, coming to the overdamped the solutions, and the critical damped solution is also there. You can I'll be anyway sharing this, so you can go through that. Next, coming to the steady state error. What is steady state error is, suppose I would want output to be something like this. For the given input, I expect the output to be something like this. But instead of the output being like this, it will be something like this. There is a error here. There is a error. This much difference is there. Suppose this is 10 volts. If I'm getting 10 volts, if I get 8 volts, the error will be 2 volts. So that is nothing but, and this continues till the infinite state. It continues till infinite state. So it is steady state error. It is an error that after a very long time, whatever is the difference in the output, that will be the steady state error. It has to be after a long time when the system has completely settled, and still if we find there is a difference in the calculated and the actual output, then that is referred as steady state error. Now coming back to this here, this is the block diagram of a, this is the block diagram. This will be the open loop gain and this is the feedback gain. E of S is nothing but R of S minus R of S minus B of S. B of S is the feedback. What is B of S? This is a signal which is coming from the output, C of S multiplied by the feedback gain H of S. And this E of S, and what is C of S? C of S is nothing but this signal multiplied by the open loop gain, for the forward gain G of S. Substitute this value, substitute this here. This has to be substituted for this term, and it is written E of S is R of S minus E of S, G of S, H of S. Take this term onto this side. You get 1 plus G of S, H of S equal to R of S. Now take the, if you are taking this term, this comes to the denominator. 1 plus G of S into H of S has to come to the denominator here. So E of S is R of S divided by 1 plus G of S, H of S. And for a unity feedback, it is R of S 1 plus G of S. And the steady state error, that is, as I said, it is after, that is after the system comes to a stable state or steady state, and it is after a very long prolonged time. So it is limit as t tends to infinity. What is the error? This is final value theorem, applying the final value theorem what we studied in Laplace. T equal to infinity in time domain is nothing but S equal to S tending to 0 in S domain. So that is limit S tending to 0, S into F of S. So it is, what is E of S? E of S will be R of S 1 plus G of S into H of S. Substitute that, multiply it with S, because it is S into E of S. Limit S tending to 0. This is the effect. That is, now we will have to find a different aerostatic error coefficient. There are, for depending on the different inputs, basic very 3 important input would be the step function, ramp function, and the parabolic function. So based on this, there are different errors that you can get. The errors is different behaviors. Because of the behavior, there is a error in the system. There is a mismatch in the output, desired output, and the actual output. So what are those? That they are taken as coefficients. There are three types of coefficient. That is it is called the positional error coefficient, velocity coefficient, and acceleration coefficient. First, when you are giving a step input, when you give a step input, the input here R of S is the input, and it is the Laplace will be A by S. Magnitude, step input magnitude is A. Laplace of a temp input is 1 by S, so A by S. And this is the expression. This expression to find the error, static error. This is the expression. This is the expression to find the steady state error. E of S is limit S tends to infinity S R of S divided by 1 plus G of S into H of S. That has to be substituted here. This value, that is S tends to infinity, S into R of S will be what here? A by S. S cancels. You have A divided by 1 plus G of S into H of S. Now, what is, do we have any S term here? In this part, is there, do we find A? S is not there. This doesn't have S. It is only this term which has S. So, limit has to be applied only to this part of the expression. Only here, limit has to be applied. So, limit as S tends to 0, G of S into H of S. This will give us a constant which is called positional error coefficient, and it can be represented as Kp. So now what will be our expression? E of SS will be A by 1 plus this gives a constant value, that is positional error coefficient value, and that is Kp. So that becomes A by 1 plus Kp. ESS, that is a steady state error, is A by 1 plus Kp. That is for a step input. What about for a ramp input? What does that mean? Suppose you have a step input. The output, this will be the desired output. This is the straight line is the desired output. Oscillation actual output will oscillate, and finally it will settle down. But when it settles down also, still there is a difference in the value. See, there is a difference. If this is a straight line, this is the actual output, and this will be the this is the desired output, and this is the actual output. So you see your differences. That difference is nothing but A by 1 plus Kp. Now coming to the next one, what happens when we are giving a ramp function? Ramp is linearly increasing input, and the Laplace would be, if the magnitude of ramp is A, magnitude here means the slope. The slope of ramp is A divided by S square. Substitute for here, R of S will be A divided by S square. 1S cancels, so you're left with 1S in the denominator. S tending to 0, limit, what is your steady state error? E of S, limit as S tends to infinity. Okay, sorry, S tends to 0. There is no S here term. We have a S term here and a S term, and here also in the second term, second part here. So this anyway becomes 0, and it is going to be it is like, how are we writing? How it will be S plus S into G of S into H of S. This will be the denominator, this term. S tends to 0 is, this will anyway go to 0. This will anyway go to 0. This term will anyway go to 0. This is anyway going to 0. So you have to only apply. Now the error gets decided by the second term. So S G of S into H of S. Limit as S tends to 0, S G of S into H of S. Applying this can be represented as another constant or another coefficient called the velocity error coefficient. Then now what will be the E of S value? E of S, if your ESS will be equal to A divided by S. Was in this value of S was anyway, this value was anyway 0. So 0 plus KV. So that becomes, it is nothing but A by KV. This KV was the second term, applying limit to the second term. This KV was got by applying limit to the second term. Next, when reference input is parabolic of magnitude A, then here R of S, this one R of T is A by 2 T square. The Laplace for this is R of T, Laplace R of S will be A by SQ. Substitute here, we know E, the steady state error ESS is limit as S tends to 0, S R of S divided by 1 plus G of S H of S. Substitute for R of S, that is A by SQ. 1 S cancels, you have A by S square, 1 plus G of S into H of S. Again, like the previous, that what we did, this term goes to 0 here. This term goes to 0. So you have the second term. Second term will be what? S square, that is this term. This is anyway going to 0. So S square G of S H of S. So limit now has to be, sorry, here it is this term which goes to 0, not this one. So here limit has to be applied to the second half, S square H of S G of S here. So limit S tends to 0, A by this, it is A by S square plus, it is this term, it is not A here, we don't have A is not there, it is limit S square plus G of S into H of S. A is not there, it is this, we only have S square plus G of S into H of S. Limit as S square into G of S into H of S is equal to another constant, which is acceleration error, which is Ka. So finally, again it is A by 0 plus Ka. It is nothing but A by Ka. Next, coming to the analysis of type 0, type 1 and type 2 system. How are these errors in the different types of system? What we just saw is how are the errors, what will be the errors for different kinds of input, for the three kind of input, what will be the errors what are the errors that we get? For a step function, we get a positional error. For ramp function, we get a velocity error, error coefficient. For a parabolic parabolic input, we get a acceleration error coefficient. So what are these coefficient? What are the values that we get for different inputs? Now, how are they? How are the different systems? That is different kind of different types of control systems. How will they get affected with this error? Now, what is the difference between the order and the system? The order is defined as maximum power of S in the denominator. If I have S5, S to the power of 5, that represents the order of the system. Type is defined by the number of poles at the origin. The type is defined by number of poles in the origin. Means what? We'll just come back here to the, here you see I have a transfer function S plus 2 into S plus 5 divided by S square into S square plus 5S plus 18. Suppose we multiply this S square, the denominator becomes S4 plus 9S cube plus 18S square. The order of the system is 4 because it is S power, the maximum value of at the denominator is S to the power of 4, and the value, that is the highest power of S is 4, the order is 4. But when we are looking at this, what is the solution for this equation? It is 3 and 6. So it is S plus 3 into S plus 6. Then when I write like this, here it is S square. S square means you have two poles at the origin. See, this represents the 0. This is the numerator. The numerator will give you zeros of the system. that is s plus 2, s plus 5 is 0, s equal to minus 2 and s equal to minus 5, it is representing the 0. So at minus 2, that is here, if I have here at minus 2, this is minus 1, minus 2, there is a 0, and at minus 5, there is a 0. Similarly, if we have what are the poles? Poles are given by the denominator. Denominator will give the poles of the system. They are called the poles. We have 2 poles at the origin, and one more pole is at minus 3 and at minus 6. So there are 4 poles, but 2 poles at the origin. So what is the type of the system? Type is 2, order will be 4. You have type 0. Type 0 means s to the power of 0, which is 1. Type 1, s power 1, so s. Type 2, s square. Now coming back to this analysis, performance has with respect to the different types of system. First, type 0 system. Type 0 system means with uh, this type 0 system with step input. How is it going to be? For step input? It is the positional error. So positional error will be, as we have already calculated, it is Kp limit s tending to 0, g of s, h of s. So this we have already calculated. So based on that, it is Kp is limit s tends to 0, g of s into h of s. From this, that is what we did here, positional error. See, this is the positional error. Now, this is for the step input, positional error. Apply that here and let g of s into h of s be this transfer function. Write g of s into h of s. Write this here. In the place of this, write this expression. You get this. And now apply s tends to 0. This is 0. This is going to be 0. This value is 0. This is 0. This is 0. And this is 0. So what do you have? 1. And we have here, what do we have here? When these tends to 0, here we have 1. This is 1. This is 1. And this is 1. So k, this will be k, then into 1 divided by 1. So it is nothing but k. This value will give you k. So kp is k. So now what is E of SS steady state error? The steady state error for step input, what was the steady state error? A plus kp. What was kp here? What is kp here? Kp is nothing but k. So it is A by 1 plus k. A by 1 plus k. That means as type 0, when you are giving a step input, the output will follow the input with an error of A plus 1 plus k. This is the input, your step input, and this is the desired value. Sorry, this will be the for the step input, this will be the desired output, and this is the actual output. And you see there is a error here. We see there is a error. The output isn't matching with the what we get. It does not match with the desired output. There is a difference, and that difference is not equal to A by 1 plus k. Similarly, for type 0, what happens if we give a ramp input? Ramp input, what is coefficient? It is the velocity coefficient. Okay, so error coefficient is velocity coefficient. It is limit s tends to 0, s into g of s into h of s. So now here, what happens here? When you're substituting, again you substitute for g of s. Then when you're substituting, you have 1 plus you have those values here for g of s. You have to substitute s into 1 plus t1s, then into t2, it is 1 plus t2s s divided by, again you have 1 plus tas into 1 plus tbs. This is the G of S value. S tends to 0, what happens? When you're tending these values, S tends to 0, S tends to 0, this is 0. Again here, there is a S term, this is 0, this is also 0, this is also 0. Again, S is also 0. So finally, the output will be equal to 0. The output is going to be 0. So this value is 0. KV is 0. What is ESS? The velocity error coefficient. Velocity error coefficient was this velocity error coefficient KV, and E of S error, steady state error due to this was A by KV. So now substitute KV for a type 0. KV value will be 0. A by 0 is nothing but infinity. Means what? Will never follow the ramp input. Whatever your actual output is like this, your actual output, your actual whatever you have to use, the desired or calculated is something like this output, but you are getting output like this. It is going on increasing. The error does not decrease itself, but rather it goes on increasing. So it is infinite, it goes on increasing. So there is no way that it comes nearer to your desired value. Similarly, what about the parabolic, this one? When you are giving a parabolic input, what happens here? Again, it is the same thing, because you have a s square. S square, this tends to 0, this becomes 0. 0 into any value is 0. Again, the steady state error due to the, what is this error coefficient? Acceleration error coefficient, Ka. A by 0 is infinity. Again, the same case. Uh, the error goes on increasing rather decreasing. Next, coming to the type 1 system. And when for type 1 system, when you're giving step input, again it is nothing but the positional error coefficient. So what is positional error coefficient? It is S tending to 0, G of S into H of S. So that is K. All these values of S goes to 0, but you also have a S here. So K by 0 is nothing but infinity. A by infinity is 0. A, this is 1 plus infinity, is nothing but infinity. A by infinity 0 means what? There will not be an error. The output will try to match with the given or calculated value. With ramp input, what happens? It is nothing but here this value will be S into G of S. G of S value, whatever equation, the entire equation that we have. So for this, your ramp input, what is a ramp input? It is nothing but S. SS cancels, you have K here. So it is A by, the velocity error coefficient is K. A by K, steady state error will be A by K. That is, for a ramp input, this will be the desired value, and the actual value, there will be a difference in the two outputs. With parabolic, S square, this denominator, I mean this value, S into this, anyway it will give you 0. So A by Ka, it is nothing but 1. A by 0, it is infinity. That is output. There is no way that the output will be anywhere nearer to the desired output. Type 2 again with step input, it is the positional error. Positional error is S tending to 0, G of S, H of S. G of S into H of S is this value, S square. So here what will be the S, all the S will go to 0. Again, this is also going to 0. So it is infinity. K by 0 is infinity. A by infinity is 0. Means there is no error. The output and input, they will match. Then with ramp function, this is G of S is anyway here. This value is, you have one S in the denominator, S divided by S square. So S and 1S cancels, you are left with 1S. There is 1S in the denominator. So that value of S will tend to 0. So that will give you 0. As S tends to 0, this becomes 0. So any value by 0 is infinity. A by infinity is 0. That means again here also there will be no mismatch in the actual value, desired and the actual value. The error will not be, ideally it is 0, but even if there is an error, it will be very minimum. Then coming to the next one for the parabolic input, now the error coefficient is the accelerating error coefficient. It is s square into g of s into h of s. Here s square, it cancels, so you have k, all these values, s value goes to 0, k, it is a by k, k is k. So there will be a, definitely there will be an error in the out. There will be a that is difference in the desired and the actual output. So like this, we have we will have to calculate. There are the problems also. These problems we will discuss in the next class. What are the error coefficient, and and how these error coefficients have to be applied for different types of input. That is for type 0, type 1, and type 2 in system. How these error coefficient gets applied, and what will be the steady state error. Now we'll continue in the next class.